Hello, hello everyone. In this lecture, we'll be learning about three-phase uncontrolled rectifier. We'll be learning about both the half-wave and full-wave rectifiers. Now, at first, we consider the three-phase half-wave uncontrolled rectifier. The circuit is very simple. We have three lines over here, three phases over here: VA, VB, and VC. They are connected to a diode, and the output of the diode, shorted output of the diode, is connected to our load, and that is connected to our neutral. Now here, in order to determine how it works, we will be using an analogy. That is, for example, if we have a connection like this, we have three diodes and we have a load over here. Now here, if there is plus 3 volts here, plus 2 volts here, and plus 1 volt here, what will be the output? V output. In this case, the output will be plus 3 volts. We are considering the diodes are ideal. The output here will be plus 3 volts. That is, the maximum input will be mapped to the output. So this operation will be followed here. We have learned this this is basic circuit law, because even if we consider a voltage drop across the diode, here it's plus 3, so here it will be 2.3. If the voltage is 2.3 volts here, this becomes reverse bias, this also becomes reverse bias. As a result, only current flows through this. So as a result, in these three diodes, only the diode that will be conducting will be the diode which will have a greater voltage here. When VA is greater, VA will be conducted to the output. When VB is greater, VB will be conducted, and when VC is greater, VC will be conducted. So we can see that here we have drawn a three-phase curve. This is our VA, this is our VB, this is our VC. So output will look like this. Here output will just follow the output envelope. Here VA is larger. As a result, the output will assume this curve. When output reaches here, VB becomes larger. As a result, the output here will be that of similar to VB. When it reaches here, VC becomes larger and the output will be similar to VC. As a result, the output will look something like this. So it is to be noted that here the output has started looking like VA between 30 degree and 150 degree. That is, 30 degrees pi by 6 and 150 degree is equal to 5 pi by 6. These two things should be noted. These two things should be. Now let us look at the input current waveshape. The input current waveshape we see, let us first consider from 30 degree to 150 degree. We are dividing it in separate groups. So we see input current, we have this. We have three input currents: IA, IB, and IC. We'll be looking at them separately. This is our IA, this is our IB, and below we draw IC here. Now from 30 degree to 160 degree, what happens is 150 degree, what happens is we see that the output voltage is equal to the voltage through A, through the phase A. That is, the output voltage, this is the this voltage, that is, the current is flowing in this direction and no current flows in this or this direction. As a result, the entire time of the circuit, only current will flow through IA and no current will flow through IB or IC. As a result, current like this will flow through IA, IB will be 0, IC will be 0. From 30 degree to 270, from 150 degree to 270 degree, what happens is the output voltage is equal to the voltage of phase B. As a result, here we have the voltage of phase B here. As a result, current flows in this direction, no current flows through A and no current flows through C. As a result, IA is 0, IC is 0, IB will have a value. Here we have IB, IC is 0. Similarly, in case of in the third part of the cycle, we have C, phase C, which conducts. That is, the diode D3 conducts. When the diode D3 conducts, there will be a current through IC. The current through IB will be 0. IA will also be 0. As a result, the output, the input currents will be entirely non-sinusoidal. For 120 degree, IA will have current and IB, IC will be 0. Next 120 degree IB, that is the phase B, will be supplying the current, and next 120 degree phase C will be supplying the current. These will be the current wave shapes. I have drawn it like this in a rough way. The current wave shape will be similar to the voltage wave shapes, that is, will be similar to this and these. The current wave shape and voltage wave shape will be almost similar, only the magnitude will differ. Now let us determine the average value for a half wave uncontrolled three-phase rectifier. So in case of three-phase uncontrolled half wave rectifiers, we have from 30 degree to 150 degree, that is from pi by 6 to 5 pi by 6. We have output is equal to VAN. VAN means VP, V phase. So from pi by 6 to 5 pi by 6, we get V output is equal to VP sine theta. Why are we considering from pi by 6 to 5 pi by 6? Because this over here gives accurate sine theta result. All the other wave shapes will give shifted sine theta, which will bring a phase shift, which will bring a little difficulty in our calculation. So we are choosing this. Now if we are choosing this, we know our VDC is equal to 1 by T integration of 0 to T V output dt. We can write 1 by 2 pi, since 2 pi is the total period, integration of pi by 6 to 5 pi by 6 Vp sine theta. Now one thing is to be noted, that this Vp throughout an entire cycle, this same thing is repeated thrice. As a result, we have to multiply a 3 here, because we are considering only 120 degree. If we have to consider the entire cycle, that is the 360 degree, we have to multiply a 3 here. So from there we have 3 by 2 pi, we multiply Vp, and here we have integration of pi by 6 to 5 pi by 6 sine theta d theta. Now sine theta is equal to minus cos theta, so we get minus 3 Vp by 2 pi cos theta pi by 6 to 5 pi by 6. If we modify it, we get minus 3 Vp by 2 pi cos 5 pi by 6 minus cos pi by 6. Now we get minus 3 Vp by 2 pi cos 5 pi by 6, that is cos 150 degree. We know cos 150 degree is equal to minus 3 by root 2. Sorry, minus root 3 by 2. Again, cos 30 degree is root 3 by 2. So minus root 3 by 2 minus root 3 by 2. So now this minus over here with this minus will get cancelled, and we'll get, and half of root 3 plus half of root 3 will just give root 3. We'll get 3 root 3 V phase divided by 2 pi. Again, if we modify it, we know root 3 V phase is equal to V line to line, so we get 3 VLL divided by 2 pi. So VDC, or the DC voltage, is equal to 3 of the line to line voltage divided by 3 times the line to line voltage divided by 2 pi. Now let us consider three-phase full wave controlled rectifier. How the full wave controlled rectifier works. Now the earlier principle that we have used to describe the three-phase half wave uncontrolled rectifier still follows in case of three-phase controlled rectifier. So in this case here, if we have 3, here we have 2, here we have 1, then output V output will get 3. Similarly, if the case is opposite, we have the diode pointed in opposite direction, and we have 3, we have 2, we have 1. The V output over here will have the minimum value, because if this is the minimum value, this has to be 1.7. If this is 1.7, this becomes reverse bias, this also becomes reverse bias. As a result, V output will have to be minimum value. So we are considering ideal diode. As a result, V output will have to be 1. So in this configuration, the V output will be the largest value of the input, and in this configuration, V output will be the smallest value of the input, which will be useful here. So in this case, in the earlier case we had considered phase voltage, here we'll be considering line voltage. How line voltage? Suppose at one point of time VA is high, so current comes from here, goes to D1. It cannot go to D3 or D5 because the diodes will be reverse biased. It goes to here, and it has now options. It can either go through D6 or D4 or D2. It can actually never go through D2 because it will eventually reach VA. It will have to choose whether the current will go through D6 or D4. Now the current will go through D6 if VB is less than VC. Current will go through D4 if VC is less than VB. That is, whichever component of the current is low, the output will whichever component of the voltage is low, the current will follow that component. If we consider it again, we can say that if we consider the line to line voltages VAB, VBC, VCA, VBA, VCB, VCB, VAC. If we consider the line to line voltages, whenever a single line will have a higher value, or single line will have a higher voltage, the output will follow that. So what does it mean? It means that if we see a three-phase line to line voltage curve over here, we have VCB. From 0 to 60 degree, we can see that VCB has the highest value, so the output will follow VCB. From 60 degree to 120 degree, we see VAB has the highest value, the output will follow VAB. From 120 degree to 180 degree, we see VAC has the highest value, so output will follow VAC. Again 180 degree to 240 degree, output will follow VPC. So the output here will follow the highest value of line to line voltages. So the output will kind of look like this, will kind of look something like this. Here we have our 0 point. The output will look something like this. Each of the component is actually the highest part of the line to line voltage. Now let us look at the current wave shapes. We know the current wave shape will follow this pattern. The voltage wave shape will follow this output pattern, and this will help us determine the current wave shape. How it will determine the current wave shape? We know that since this is a three-phase system, we have to measure IA, IB and IC separately. So at first let us look at this point here, VCB, the voltage is VCB. That indicates that at point C, at C node the voltage is higher, and at B node the voltage is lower. So current goes from C node and comes back to B node. So if we consider that the current through C node is current going from C node, or going out as positive and current going in as negative, then in case of VCB, our C will have a positive value of current till 160 degree, or C will have a positive value of current IC, and B will have a negative value of current. This is our IB, and IA will be 0 because nothing flows from A direction. In the second half, from 60 to 120 degree, we have output is equal to VAB, that is current starts from A and comes back from B. As a result, B will be negative since currents come back to this terminal, and A will have a positive value of current, and no current passes through C. In the next 60 degree, that is from 120 degree to 180 degree, the output current is equal to VAC, that is current leaves A terminal, A phase, and current comes back into the C phase. As a result, the current at A would be positive, and C will have a negative value of current, and B will have 0 value of current. And the next stage we have VBC, which means that current goes out of B and comes back through C. So for next 120 degree, we have a positive current through phase B and a negative current through phase C. For the next 120 degree, we have VBA, which means there is a positive current through B and a negative current through A, VBA, and C is 0. In the next we have VCA, so we again have a positive current through C for next 60 degree and a negative current through A. So current wave shape will look like the following. The IA will look like this. IA will look something like this. IB will look like this. Here we have current, then we have 0, then here also we will have two current peaks, and here we have 0. And IC will look like this. Here this is 0, and here we have negative side, and then again we have 0 and again positive peak. So these are the current, these are approximately the current wave shape of a full wave rectifier, full wave uncontrolled rectifier in 3-phase configuration. Now we have to find the average values. In order to find the average values, VDC is equal to 1 by T integration of 0 to T V output dt. Now V output is equal to VAB, or V line to line, that is VLL sine theta. From here we have 60 degree and here we have 120 degree. So 60 degree means pi by 3 to 180 degree, 120 degree means 2 pi by 3. So from pi by 3 to 2 pi by 3 we have the value of VLL sine theta. So we will get 1 by 2 pi integration of pi by 3 to 2 pi by 3 VLL sine theta d theta. It is to be noted that this same thing is replicated once, twice, 4, 5, 6 times. So as a result, a 6 will be multiplied. From this we can determine VLL divided by 3 VLL divided by pi minus cos theta pi by 3 2 pi by 3. From this we get minus 3 VLL divided by pi cos 2 pi by 3 minus cos pi by 3. Now minus 3 VLL divided by pi. Cos 2 pi by 3 is equal to cos 120 degree. Cos 120 degree is equal to minus half. And cos pi by 3 is equal to cos 60 degree. Cos 60 degree is equal to half. So we have 1, that is we will have this minus and this minus, and this minus will become plus. We will have 3 VLL divided by pi. This is the expression of VDC. That's all for 3-phase uncontrolled rectifier. In the next lecture, we will be learning about the controlled rectifiers. Thank you.